Hey guys, my name is Jan. Welcome to another video on this channel about the Minuteman project, where we're trying to find out, is printing a 3D-Benchy in sub than 1 minute even possible? So in the last couple of episodes we were focused on getting the motion system up to the task, finding out where the limits of stepper systems are, and now we're going to revisit the Hotend situation and finally get some filament extruded. If you remember, last time we were on the machine actually 3D printing, we built this abomination of a Hotend. Today we're going to do an even more outrageous version of it. So somewhere in this piece of copper we find another split Hotend, which I've designed over the past few weeks and used all the information that were available for me from the initial tests on here. What you can see here is a top-of-the-line extruder system from the Swedish company Bondtech. They actually provided this for me. This is the LGX Pro with the dual large gear inside. They provide one of the highest push forces of extruders on the market. This is combined with a slice engineering cold end and also bimetal heat break. We're going to connect this and a lot more to two pieces which we're going to carve out of this solid copper block. And yeah, since we're madmen, we're using a lot of this and also some more which is on the bench behind me. So this episode will be all about milling this one-of-a-kind Hotend, getting it set up on the machine and seeing where the true limits of filament deposition really is. So stick with me for another episode on the Minuteman channel. Let's roll the intro and let's get started.
Da 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 da.
Alright, so before we actually go down to the machine, let's talk about the Hotend for a quick second so you know what I'm building. Toggled visibility of all the accessory parts, and we're just going to focus on the main Hotend. So as we tested the last time, and I think this is a pretty unique and performant approach, we're going to use a split piece design. So as you can see, these are two parts which are clamped together by all these screws. We actually do have two heating zones. So the upper part will be the one where filament comes in and will be heated as quickly as possible. That is its main job. And we can control these two zones pretty much independently, and they have their own control loop. As I said, this is going to dump as much heat as possible into the filament. At the exit down here, we want to have a set temperature and have the filament at a very low viscosity to cause very little back pressure in the system, because pressure is what actually is going to limit our performance of the Hotend and what actually is coming out of the nozzle here. So then the second heat zone is there to actually give this system a lot of control, because either way what's coming out of the top part, we're gonna use the tip heater to make it an even temperature, because if we have the capabilities to heat it up to 280 degrees, that helps our pressure and we can use it to melt the filament evenly. But every degree on top that we add to the filament, we have to cool down again, and that is not helping with our third main issue, the cooling situation. So this heater here may actually be a cooling system. This may be drawing temperature back from the filament, and we're going to experiment what the best settings for printing a Benchy actually are. Even though this is a quite small heater, this is 10 by 10 by 20 millimeters, it will feature two ceramic heating elements on here, which are combined of 100 watts of heating power, and with an additional heat sensor in there, I think it's going to make up for a very dynamic controller loop. But yeah, the main thing is how we're going to heat filament as quickly as possible. So let's toggle the cut view. So ladies and gentlemen, this is what we're dealing with. As you may have seen in the intro, we're going to feed 4 filaments at the same time into here. And if we just have a look at one individual filament path, you're going to see that it's roughly 35 millimeters of more or less straight passage it's going to pass through. And then we're going to use this splitting technology to actually cut down the filament right in the middle. Filament or plastic does have a very bad heat transfer to its core. We actually have to do this in order to maintain a homogeneous melt. Within this 12 millimeters of melt channel, we're going to use this inner part to actually heat the core as well, and then combine this filament strain again right at the exit of this cutting section. This is going to happen 4 times at once, and then we're going to combine it into this big channel here in the middle. That is going to be our exit. Followed by the exit, there will be this stainless steel, let's call it a heat break. We'll see what the heat transfer between these two parts actually is and how independent from another we can set this. I am planning and have laid out all the materials used to have this upper part heated up to 400 degrees or something. As I said, our main priority is to have all the melt above a certain temperature when it exits this block. Whatever this temperature is, we're going to find out. Let's address surface area for a second. We're coming in with 2 millimeter bore up here. Then we're going to split that to twice 1.5 millimeters. Then we're going to combine all of that to a single 4 millimeter channel. What this basically does is to have the surface area the same throughout the whole hot end. And what that does is to have melt velocity at a constant throughout the whole process of getting 4 filament paths in there and combining it to the nozzle. And by doing that, we should have the most laminar flow of them all, which is like the sign for the lowest pressure in the system. The pressure, of course, will have its spike down here at the nozzle exit, which is going to be limited by the 3D-Benchy rules, which is 0.5 millimeter. This is pretty much the limiting factor. If we would have a 1 millimeter bore or something on here, we could expect a lot more of melting capacity, because we're limited by the pressure we can put into the system. And just to put this in perspective, the Bondtech LGX Pro is capable of pushing up to 100 newtons onto a single filament strain, and that is resulting in over a few hundred bars of pressure inside that channel. Some of that will be lost due to friction on these channel walls, but most of it is going to end up pushing this material here out of the nozzle. And once we're at it, we're also going to machine our own nozzle. This will, accepting this 4 millimeter hole and then conically go down to like 2 millimeters in here, have this angle a bit more opened up, and then exit through 0.5 millimeter of bore. Yeah, so now we're going to the machine because there is a lot of cooling involved and very small diameter tooling. You ain't going to see shit, and that's why we're talking here before. Stick with me while I'm going down to the mill. Alright, meet me again in the Mao machine. I've put our round stock into some soft jaws and machined the first side flat. And now we're gonna flip it and then mill all the features in there, carve it out, and then we're gonna do the mutual features to both of the Hotend halves. Alright, let me get you updated. So I got the part to the point where we have all our drillings in here. The 4.2 millimeter holes are for M4 screws, which are going through both of these pieces, and the 6 millimeter holes are for the heat cartridges, and this single 2 millimeter hole is for the temperature sensor. And now we're going to do what this mill can do best, running very small tools with loads of spindle speeds. So talking materials, why we're choosing copper seems to be pretty obvious. Copper has one of the best heat transfer values in all the materials. There would be silver and something else, I guess, which is slightly better, but I think this is good enough for what we're doing here. And this is the simulation of what's about to happen. So what you're seeing here is a 2mm ball nose end mill, and it's basically gonna go in there, take very small cuts, because copper is kind of prone to basically weld itself to the flutes of the end mill, and since this machine is only 6k RPM, I kind of don't have the RPMs to run these tools out. And yeah, this is going to do all this work down here and then up here, mill those channels, everything that is in 2mm territory. Then it's going to do a 3D contouring of that 4mm channel here as well. And then we're going to switch to 1.5mm tool, which is essentially running at even less surface footage. I think it's 30 meters per minute or something like that. You could run these tools with 300, I guess. But this 1.5mm tool is gonna carve out these guys. Then it's up to a 6mm end mill that is going to carve this out, leave some tabs there, and then we can get this out with the bandsaw. So let's do that. Let me see if when I can give you a few snippets of the cutting, but it's a very small tool and it's going to be pretty much submerged in water, so there's no real point in doing that. We're making good progress. Don't know how the camera is picking that up, but I'm quite happy with the results so far. So all the channels are in, all the pockets are milled. Now comes like the part where I'm a bit nervous about. This is going like full slotting in here. Gonna run outside of these two parts and they will just be held by some tabs later on. I can then cut the tabs with the bandsaw, and when I flip these parts over and cut the chamfer on the back, the tabs are completely gone. At least that's my plan. So let's see if it survives that, and then I can finally get these parts out of the mill under a microscope, etc., and we can have a closer look. Yep, that did work. So as you can see, it is just being held by a few tabs, around 1mm worth of material. Get over to the bandsaw, chop them out of there, and then give them a real quick lap to get rid of the small burrs. Then put it in, I think, some soft jaws and machine the other side. So this is where we're at. Two identical brothers for now. I just gave it very fine lap to get rid of the burrs. There are a few things I don't like too much, but I think we're okay with that. As you can see, these spot drills are a bit deeper than I would like them to be. Also, I put in my signature mark on here. I selected the wrong direction for the chamfer cutting. All the others were okay. This one was not. And if this would have taken 0.5 mil more of an approach pass, there would be a channel and this would be scrapped, but I think we're okay for now. So that worked out. I got both of the halves at least prepared, and again quick lapped and deburred. So they fit together quite nicely starting from this point. What we're going to do next is, again, I got some gauge pins here, and we're gonna take, guess, the 195. It's almost impossible with one hand. And we're gonna align the whole thing just like the last time, and then we're gonna meld some mutual features. So basically I'm gonna put some screws in here to fix this all up, and then we're gonna put this in the milling vise and see that this is in line with the spindle axis, pick up the point, get some M6 thread in here, do the same here, and do some end work here, and then we're basically able to get this all put together. This is hopefully the last setup for this part, and when we have a look at the simulation, it basically gonna just chop off the material I left on here, cleans everything up. Then I'm gonna drill the hole where the second like heat break comes in, chamfer everything, and then put two M3 holes in there to attach everything. So let's hope last operation doesn't screw it up, and then we can go and machine the other parts. And we're going on in our quest. So I got the next part finished. Let me change the view. So this is basically the top heater part, or nozzle heater, or just a tip, whatever you want to call it. Or this came out quite nice, but then just ask the machinist at the end of the day, you want to get done with your job and tell yourself you don't need to spot drill this hole. With all the lubricant I didn't really see it, and it ran into this bore, but for what it's worth it doesn't matter. I drilled a new one here that will work out fine. So I guess we got the very tip done, and next up we're gonna go to the lathe, and I already did a setup because we need like the stainless steel standoff or heat break. Gonna do that from that grounded rod. I'm gonna drill and ream a 4H7 hole in there, maybe polish it a bit, and yeah, this will act as a connection between the two copper parts. Well, that worked pretty darn good. Better not drop it, and yeah, it's the size of a moderate chip here around the lathe. Alright, the last part we need to make before we can actually put everything together and have a closer look is to enlarge the entry diameter of that nozzle. I took a generic 0.5mm nozzle and chucked it up in the lathe. There are a few things in terms of nozzles I would like to test. We're also going into detail why I don't think a CHT nozzle isn't the best choice for this application. But we're gonna do something like this, and this involves a teeny tiny boring bar. So something like this, we're gonna enlarge the entry to 4mm and conically taper off to 2mm. And yeah, then we have a nozzle to put on the machine for the beginning. And yeah, then we have our reference nozzle for the time being and see where you can improve from here. I think I have finished machining all the parts for the Hotend. I mean, the metal parts, I guess. The printed stuff is up there and also ready to go. So maybe I'll have some time tonight or tomorrow in the morning to finally assemble the Hotend. So, but while we're here, let's have a cup of tea together. So, this is the recent status. This is still clamped together just by these screws for manufacturing purposes. This is the nozzle tip with the nozzle you've seen me machine. Won't be able to see that too good, but you can see it's a 4mm diameter up here, and then it's conically connected to the nozzle. This is the place where the two ceramic heaters will be attached, and these grooves are here because I'm going to attach them by some steel wire. There is a boss which accepts this heat break, and the same is on the mating side here. In case you're wondering, these two holes here do have the lowest amount of actual clamping pressure of all these screws, or where I need them the least. So I reamed these for tight fit of two dowel pins, and these can be screwed. I mean, you can put the dowels in, put all the other screws in here, take the dowels out, and then also put some screws in here. Because what I found out with the latest iteration of the Hotend, once this is heated up, the dowels are actually free, because the copper or aluminum, as in the last test, is expanding more than the steel. And then they actually fell out after some time. So I think I'm not gonna hustle with that again. And yeah, let's break it down and let's talk about how we finish it. Alright, so this is what we're talking about. Came out pretty good. As I said, there are a few signature marks, but I'm okay for this type of thing I'm building here. So now, let's talk about these channels. As with the last setup, we actually have a very fine splitting geometry. The way I machined these, they are naturally building some kind of a blade to actually cut the filament in half. And this came out pretty good here too. Now we could argue about what to do with these channels as a whole. So what should we do as a surface finish here? And most people would straight up say, well, yeah, polish them as hard as humanly possible, because I got access to all of that here. And we could do that pretty easily. But I have something else in mind and a theory to share. This is just a theory, and I have no idea if someone else also wrote that down, but maybe it's totally untrue, but hear me out. So my intention is to actually not polish that, at least not for the most part. I'm talking about the first section, like these 35 millimeters before the filament is actually being splitted. I want to go ahead and bead blast that to give it a really rough surface finish. My theory behind this is the following. So let's imagine this PTFE tube of 4 millimeters is of filament strain. So without thinking too much of it, when the extruder pushes the filament into our heat zone, you basically think that the whole filament is traveling down that path as a whole. But I've seen this in many other applications, and my understanding behind it is the following, that it's actually not like that. What essentially happens is there is a heat transfer in the most outer zone of the filament, and then this filament is actually kind of like sticking to the walls, and then the inner core, which isn't really up to the temperature, because heat transfer in plastics is bad, is actually pretty much moving like this. So the walls stay, and the inner core, which isn't heated up yet, is traveling along its path or is being pushed by the extruder. So if your channel walls are being polished as fuck, then my understanding or my theory behind this is that this outer part doesn't really stick to the walls very good. It is kind of like doing a stick-slip effect down there. And what you end up with is a pretty chaotic movement of this whole strain. What I'm trying to find out is if we do intentionally rough up the surface, at least in the very upper part, can we have that outer part mostly being stationary up there and can have this pushed very controlled? Because the friction of this inside here can basically be described as fluid friction, while this isn't to the outer wall. So my theory is that this is being accountable for the lowest back pressure you can have if the outer wall is staying as persistent as possible. That does somehow change after we pass our splitting section. So my calculations come out to this is at our highest feed rate. All the material should be melted homogeneously at this point where it exits the splitter. And now we're just going to combine everything, make it flow very controlled, and let it settle throughout the whole melt to gain a very even distribution of temperature. So that's why I think it is then beneficial to polish this part, because we don't have that situation that part of the filament is a lot colder or has a different viscosity as the rest of it. So I'm not a native speaker, and I even struggle to explain this in my native language, but I hope you got the point behind this. And long story short, I'm gonna try to bead blast these upper parts, make them really rough, and then have this lower section polished to a fine surface finish. And then I'm gonna give it a last lap, so these mate together perfectly and form a very tight seal, and get all these screws in here. So that's for now. See you at the bench upstairs. Alright, this is the morning after, and I think this is still the original. And the other side I have, at least for now, finished. I polished the section towards the nozzle and left the upper parts untouched, as well as gave it a last lap to make these surfaces mate each other pretty good. This is the surface finish on the front. Nothing too fancy. I got carried away enough with this project already, so let's not make this a mirror. But I think those came out pretty nice. Yeah, one thing I forgot to mention yesterday, please go ahead in the comments and give your 2 cents on what you would have done in terms of finishing, if you would have left that untouched or bead blasted it just like I did, or polished these channels as well. We can have a look on the microscope to see what I'm talking about. So as you can see here, these are the channels straight after bead blasting, and this is exactly the effect I was hoping to get. Let me zoom in a bit more. It's a really roughed up surface, but very evenly distributed. If my theory is true, I think this is very close to a really good surface finish to actually prove my point. And then if we lay the two sides next to each other, this is still the unfinished piece, and here comes the polished one. You can see the difference it makes. So, and as I said, I think after leaving the splitters, we have to have a homogeneous melt. And I think from this point on, it's beneficial to actually have that as a polished channel to make the melt flow as easily as possible without creating too much of a back pressure. So I'm going to do the second one. I'm going to give you a few insights on how I did this polishing, because I think especially in copper this isn't too easy, and then we can finally put this all together. Okay, a quick summary of how I do the polishing on this part. So basically polishing and lapping and all these methods can be distinguished by two ways, let's say that. There is polishing with unbound grain, which is stuff like this diamond paste, and there is with bound grain, so basically your standard emery cloth. Usually what you do in lapping is to have these unbound grains and use something as a lap that basically gets these particles embedded into. And when you're working with tool steel or something like that, which is my typical application for polishing, you can have a range of lapping materials: brass, copper, bronze, aluminum, rubber. They all work exceptionally well because they are way softer than the tool steel, and the unbound grain particles, like these diamonds, will actually embed in the softer material. And then you can use a very soft material to work on your hard steel. In this case, it is a bit of a problem because this copper is pretty soft. In my experience, polishing copper is not the easiest task in the world. So what I settled on is for these, because I don't really have tooling for that size of diameter. My usual work is way larger than that. So what I basically came up with is toothpicks. These fit pretty nicely in my die grinder's chuck. I can use the bound method with some very fine 1K grit emery cloth superglued to it. That's for the bigger channel. I can reach those areas with that. And for the smaller channels, I toothpick, have the edges rounded off a bit, and then use either the diamond lapping compound or some polishing compound. This doesn't work exceptionally well because the particles don't seem to be embedding too easily into the wood, but wood itself is kind of an abrasive material, so if you have a bit of patience, and that's what working with copper is all about, then it's kind of working pretty good. So you saw the results on the first one. Let me do the second one, and then let's get finally to assembling this beast. Meet me at the bench. So I think it is finally assembly time. I do have all my machine hardware up here. And while we're at it, let's talk about the extruders we're using. Last time I had these really old, like Costal pusher assemblies from 1996, I guess. And those were part of the problem because I couldn't keep up with the pressure that we need inside the hotend with the old 4 intake hotend I've built. So this is what Bondtech and Slice Engineering actually sent me free of charge. I didn't receive any additional money to review this, but I haven't tested those on the machine. But I think from this standpoint on, I really like the appearance and what they did with these components. So let us have a quick go through all the components, and everything you see here is basically here 4 times. So starting with the heat break, this is a bimetal one. It is copper on the outside, stainless steel on the inside, basically for the best possible heat transfer, both when you need good conductivity and when you need bad one. All of that is coupled into the Slice Engineering copperhead heatsink with the screw mount. So basically this upper part, these are both aluminium anodized. This upper part belongs to the extruder, and this connects seamlessly to the cold end. And why I chose this one specifically is because of this style of connection between cold end and heat break. Because I have 4 of these, so basically when I have my whole assembly, I can't really screw those in because those are rigidly connected. So what I can do is get the heat break inside of my hot end assembly and just put on the heatsink and basically lock it in the very place I need it to be. So moving up, this one butts up in here. This screw clamps it. And on top there is this PTFE tube, which gives a very close connection to the actual extruder gears. And also I removed all the screws, so let's have a look in here. Alright, so I think this is a pretty neat solution for setting the distance between these 2 driving gears. This is done by this knob on here, and it's like 5 positions. And this will help me a lot as well to find an even setting between all of those 4, because I can just have it in a similar position locked in, and I know the gripping force will be equal among the extruders. So this is in their LGX product line, the dual large gear extruders. And of course they have potentially the highest gripping force because they have the highest contact area. And you don't have to pinch down on that very small contact area. You can have that distributed over a larger area. These will push up to 100 newtons or 10 kilograms, which is a lot. Stefan from CNC Kitchen already tested those and confirmed the results that were on the Bontech page. And then what's also pretty neat about this is the connection to an existing stepper. So this is all metal inside. This is an SLS nylon printed part, which is of very high quality and does fit very nicely. This is basically the whole package. This motor is specifically chosen for this application, and they told me, sorry for the noise, but someone's outside with a weed eater. But yeah, they provided this motor as well and gave really good instructions on how to drive them. So 1 amp is basically all you need to have. Everything above will just buckle the filament. And this is exactly the information I need. It also comes with this very nice booklet. I would have wished for earlier attempts of with different printers, so it basically gives you retraction settings and whatnot. This isn't much, but this is all you need to have this set up. And where I had to chuckle was the LGX Pro for creators with more intense applications. If that doesn't fit for my cause, then for who? This is one of the 4 drivetrains up here. I'm gonna set everything back together and then get to assemble this beast and put it on the machine. So I thought there were no words needed for that moment. I'm pretty hyped. Let me put on the other stuff like electricals, there are fans, heater cartridges, mounting. A lot of screws have to be put in, but got a few hours left today. I'm gonna finish this bad boy up so we can put it on the machine. So we could put it on the machine for tomorrow and do a testing day. Guys, I think we're done, at least for now. So oftentimes you see stuff in CAD. I've been designing this for a couple of hours, let's say that. And when you see it in person, I'm pretty hyped. So let's have a look. Let's have a look what we got here. If we turn this bad boy around, can see that there are quite a few cables and lines are going in and out from here. So all of this will be wrapped up in some kind of a sleeve going towards the power supplies and controller, etc. What we got here, these are of course the motor cables and fan connections. Up here we're running heater cartridges. 5 of them. These are 24 volts, 50 watts. The last ones I had were 12 volt units, and I can power everything by 24 volts now, so it would make sense to upgrade these as well. There is a combined heating power of 250 watts. Also, as you can see, we have 4 of these paths running down here. So each of those path will have basically a heater to the left and to the right, so the distribution will be pretty even. The thermistor is measuring the temperature right into that splitting lane, pretty much 1 millimeter away from the channels. So this will be a pretty good measurement. As lots of people pointed out, having too much of a thermal mass is kind of a problem because temperature drops right where you need it. But at a different point where you pick it up with your sensor, it will be very delayed, and so the whole controller loop is messed up. I was aware of that, so that's why I intentionally designed it to be a 2 heating zone element. And so we're gonna have a closer look at just the tip here, because there is so much stuff going on. I basically wanted this to be as small as somewhat possible in terms of heat capacity, so the controller loop will be as accurate and dynamic as possible. So this part you can see up here is basically an SLA printed part from a high temperature material, and this is kind of the heat sock situation I have on here. I debated with myself if we should go the silicon route, but I think the solid approach has a few more upsides than the silicon one. So in a later version this will be different. I can reprint those anytimes, but right now I have to unscrew the nozzle, which doesn't make too much sense. I just forgot about one direction. Let me get the nozzle out. All of our cooling is coming from behind, so that's the main reason. This should shield the nozzle itself, and it is sitting in this like bracket, and just the tip is sticking out like 1 millimeter. So we don't want to blow all the cooling air on here and then cool down our nozzle, because the nozzle isn't really a thing of a temperature control loop. So I have to work on tolerances here, and I will change the sliding direction, I guess, but this can be like just put on here. But I have to find a way so the nozzle can be still in place while this slides on and off. What you can see here are 2 ceramic heating pads. These are also 24 volts, 50 watts each. So this small little block also has 100 watts of heating power. This is not the final wire I used here. I can't find the one I've intended to use here. but it will be fixed in that way. So as you can see, there are grooves machined in here, and I can basically lay a steel wire around the heater blocks and just twist them in the end. That way the cable pulls it tight. Okay, in terms of mounting, I chose to go that way because in my previous attempts it turned out to be a problem to actually mount to the hot end itself. This is a pretty big boy. We want it as rigid as possible. So I took out the original screws, M3 screws that go into the NEMA housing, and solid printed an adapter plate which use this bolt pattern and have this very rigidly connected to everything. One last thing, you may see this is pretty much a complete unit, except for the cooling part. And cooling is something very interesting, because as I said, cooling will only come from behind. This is my latest prototype. In all the earlier versions of the cooling situation, I tried to get as much airflow as possible. Maybe I will put in a video of the latest blower which uses shop air. And I personally think this is not the way to go, because we are just blowing filament all around, and like if you have let's say a nail or something at a very high temperature and you dump it into a bucket of water, it does not make a difference if this bucket has 10 liters or 1000 liters of water available. The heating or the cooling capabilities of that water will essentially be the same. And I think the same goes for air. So with this approach, I'm trying to bring air at the exact position it needs to be. So this would probably be somewhere like this. And it would just blow air. I mean, of course, with the sock installed, it would just blow a thin sheet of air straight to the filament that is being pushed out of the nozzle. That's why we need that shielding so much, to not blow the nozzle cold, but to have actually the filament that has just been deposited being cooled very efficiently. And also maybe we're going to do not only by air, we're going to use some different method of or different media on there. But we'll not go too much into detail. I've actually written a few mails back and forth with Mike from the Needed Make It channel. I think I'm not going to go into any detail on this and let him do the testing and have like this thing or this method compared to a regular fan solution. So let me do the wiring, let me put it on the machine, then we'll not talk about this again, and yeah, do some extrusion tests. So I think we're there. Have a look. So for now I got all the cables hooked up to the controller. This will be like done properly eventually. Basically everything is hooked up. I already had like 75 degrees on both heat zones. That worked out. I put in some filament. This is like your standard King Rune PLA Plus. I think we're just gonna go for it and extrude some material. Like with each click, I'm gonna put 6 meters of extruded filament out there. I'm gonna click it a few times. Let's see what it does. Alright, this is the first skipping step I've heard so far. We're at over 300 cubic millimeters flow and just at 220 degrees. I did some just fooling around yesterday and it's looking really promising. So let's have a look at here. As you can see, this hot end was like heated up for an hour or something like that. And you can see it's gone through all of its oxidation colors. I Could have and maybe wanted to nickel plate it, but as you can see, all of my power supplies are bound in here, so that would have been quite the pain, and I wanted to test if this is working or not. If we have to change something, I can do that and then nickel plate it. If not, maybe I'll just leave it until I have to maintain it at some point, but for the time being, I will leave it here. First impression about the whole setup itself is really darn good. It runs butter smooth, there is no strange noises, and there is one hell of a material coming out of here. So I was fooling around for just a few minutes yesterday, and I just put this on the scales and was 40 grams of material in a matter of minutes. So let's put that into scientific numbers here. One thing I like extremely well about this extruder setup is this quick action lever here for setting the tension. This has the huge benefit in its lowest section. It will basically won't have any tension on the filament itself, so I can pretty much just run it dry. That was super convenient for setting up the motors. I did some fooling around with these here, and now I have these two hooked up to one TMC 5160 Pro on the main board, and these two. So I can run each of these at their rated current of 1 amp. That's what I wanted to have for these tests, so we have the same numbers throughout the test. And these levers have 5 independent resting positions. I'm gonna put them either on position 2, that worked yesterday pretty well, or maybe I'll try to push it and put it on number 3. 4 and 5 seem to be for flexible materials, something like that. I'm gonna hit 215 degrees on both of these heating zones. For the time being, the heated bed is the big ass chamber, and the extruder section is this small one at the tip. I'm gonna rename them afterwards. So I'm gonna hit a stopwatch. Let's hope there doesn't blow a fuse or something when I give it the beans now, and we'll see how long it takes to fully heat up. And let's just hit this go, 215 and 215. You will see that the extruder itself will go pretty fast. I mean, it's 100 watt heater on this very small copper block. To be noted, there is no thermal paste applied yet, so everything will be a bit faster in terms of heat transfer, but yeah. Let's just have that in a time lapse and see how long it does take the big block to reach working temperature. I did the testing with just having the upper one going, how much it's going to influence the temperature of the lower one, and we can have, if it settles in, we have a temperature difference of 50 degrees. So when this was 215, this was somewhere in the 160 range. I think that's right where we need to be, because this will have a lot of active cooling, and then the difference we can actually have in there will be way greater. I've got a G-code written. It's going to extrude a set of amount of 300 millimeters of filament. When I have 300 millimeters and got 4 of them spools running in, I need to divide it, so I got the exact amount on here. That is because each of these channel is 65 to 70 millimeters of filament, which is sitting in the hot end and may be hot as hell. So we want to purge that. These are the flow values I'm actually going to be testing in my G-code. It's 100, 125, 150, 175, 200, and then go up in 10 cubic millimeter increments, and I prepared for a 350. Let's see if that number is realistic, or maybe if we even have to push it up. And each time I'm gonna use a tweezer and take out whatever came out of the nozzle during that time, and then put it on the accurate scale, and then plot it all over in the Excel file. I'm going to do that for different temperatures, starting at 215 degrees and work my way up maybe to 240 and 270 for now, and then we're able to draw a conclusion where the limits are for this hot end. So this is just absurd. And when we're going to talk about numbers in a few minutes, I want to have the last two included so you are able to see my testing method. The next two ones are 340 and 350 cubic millimeters a second at 215 degrees. This is purging. So I think this was the first skipped step I heard. This has the first sign of under extrusion at around, 10% of under extrusion, 1.13 grams. It should have 1.25. So let's do the last one. Again, purging. Yeah, that was another skipped step, and it's pretty hard to keep up with, like, getting the end of whatever. I mean, this isn't scientific anymore, but let's put that on the scales. Either way, it's 1.11, so down again a slight bit. Alright, so you saw my testing method, so let me get you on the screen again and we'll talk about the first results. I think that went above my expectations. As you can see here, this is the flow rate in cubic millimeters per second. This is the weight I did actually measure on the scale. Take all of that with a grain of salt. It depends on how you, like, where you put the tweezers, etc. But this is pretty consistent throughout the whole thing. You can basically see that up to a point of like 250, 260 degrees, it was straight up to nominal weight. And then I could see, and also that's visible in the video of the like 340 and 350 flow test, that right at the end it is definitely a incomplete melt, for sure. But the most interesting thing about it, if you leave out these two lines here, these Bondtech extruders are just nuts. Whatever the heating capabilities of this system actually is, they're gonna push it just right through, no matter what the viscosity actually is. So that is a very, very good thing. So basically what you can see from the graph, up to 250 cubic millimeters, it works like a charm, then it tapers off a bit, and then we actually at 330 we reach the limits of heating capabilities. I think that's where our splitting geometry is actually blocking us in terms of flow, because right there the filament isn't warm enough to actually be splitted, but the system does it anyways because there is just so much force in pushing up there. But yeah, I wasn't expecting to have that, or to be capable of having that much flow up there. Of course, we're only operating at 215 degrees, so that is just bananas. Next step will be doing the exact same test at 240 degrees, but I don't want to waste my time and start somewhere here at like 100 cubic millimeters or something. I'm gonna jump right in at like 230 or something and see how far we can stretch out our graph. I'm gonna go and extend this at least to 400. And right where I see this drop here, I'm gonna stop, of course. Also, a few things. I mean, this Hotend itself is pretty big, of course. But if I think about it, I wouldn't have been able to make it any less big, because I need all those clamping area, I need all those accessories for sensors, for heating elements, etc. And I've been very conservative on stuff I put on here. I was thinking about a whole lot range of sensors for flow and melt temperature, etc. I didn't go that route because it was just too deep of a rabbit hole. The thing is with control loops. So right as we start pushing in material, through the high heat conductivity of copper, it will actually draw out the heat from those channels very, very quickly. And it takes a few seconds to actually be measured by the heat sensor, which is right in the middle and here on like where the logo is. And then it takes another few seconds for the heating elements to actually kick on and get heat somewhere in here, up here. That is a problem of the control loop that we got going on here. So we could argue that we need to have the heat sensor way up here or whatever, but in terms of this big heat capacity, we're never going to be in a really good system. So what we would do in an extreme situation of like printing a Benchy in less than a minute, we would write a script to have those heaters being kicked on a few seconds prior to an extreme extrusion move. So let's say we can measure that it needs like 10 seconds for the heating elements to reach up here and actually make a difference. We would trigger that 10 seconds prior to the extrusion move and then have all the heating capabilities already up there and then maybe net out the temperature drop in here. But that's stuff for later on. I think we're gonna have no problems whatsoever extruding 10 grams of material in less than a minute. We're gonna try that afterwards, but first let me run the tests on those different temperatures and see where we end up, and then we can draw a conclusion for this hot end. This went exceptionally well. So let's have a look on the screen again. I conducted a few more tests, and you can see first one was at 215 degrees. The next one I did was 240 for the big block, 215 for the tip. Then I gave the tip 240 as well, so 240 for the whole hot end. And in the last one I switched back to 215 at the tip, but then 270 for the heater block. Let's talk about comparison. This looks like a big drop in here, but this is actually just the 2% line when you have a look at that y-axis. So everything above here is basically negligible, and what I think happens there is we're gonna push so hard on the material up there that it's actually going to compress, and that's what we're seeing here in the results. But as you can see, blue line 215 drops off at 320 cubic millimeters. We increase the temperature of the bigger block. We can do 340, maybe 350. If we increase both heat zones, the viscosity is being fed through the whole hot end, and we can make it 370. And if we have that upper block at 270 degrees, we can even go 380. Our limiting factor is how much energy can we push into the material inside that first 30 or 40 millimeters of filament path. And we can just offset that by going higher and higher in temperature. I could do that, except for the Teflon tape. All the materials are rated for 350 at least. So we could do that, but I think we're well above what we actually need. So I have no interest in pushing it and breaking it. It's been super reliable. Everything was tight. No weird squeaking noises whatsoever. So I'm gonna leave this untouched and do printing first before I have to do my first round of maintenance, because this isn't your standard hot end where you just unscrew a nozzle and you're fine again. This takes time to do assembly, etc. So I'm pretty happy it just works out for now. Also, you can see that even in the latest test, the heat gets drawn pretty quickly out of that tube. And I've been doing some other tests with continuous flow, and the heaters are pretty much working full blast to maintain like 270 degrees on the big block. What I have as performance boost is actually adjusting the voltage. So if I increase the voltage, the power will increase by the square of it. And in my last test, I found out that I can pretty much override these for a good amount. So we could add thermal paste, go on them with like 35 volts, have a lot more power on them, and yeah, basically be in the range of 400 watts of heating power, and we can maintain more flow. But it's actually a problem of getting the temperature to the right point. But again, we're well above what we need for printing Benchy's. So I already prepared a G-code for extruding the material we need for a Benchy. Let's say that's around 10 grams And I think this is fully melted. I can't touch it when it's out there, so it's thoroughly melted. And you can see the way it exits the nozzle that this isn't an incomplete melt by any means. But having a lot of headroom is never a bad thing, I guess. So in terms of the hot end, I think we're gonna finish that off right here and right now with some continuous just power blasting through it. This is what I ended up with like after 1.5 hours of testing. My spools are getting emptied by the minute, so there's pretty much filament going through here. And we're just gonna extrude some more, just for the giggles of it. I know you guys want to see this machine printing. I want to do that too. I can't deliver that in this video. This is already probably the longest one I've ever done. And we're still at a count of 1, 2, 3, 4, 5 prints so far. Next one will have a print in it. I have so much to talk about in terms of what we're gonna do with this system up here. So basically this is at 70 grams right now with thick cables. To go for our minute run with steppers, I have to go above and beyond. My current version is as stripped as you would never imagine it. And with the screws in here, I'm right about 17 grams of moving mass. So that could potentially put us in a region where we could think about doing such a run. But then again, I have to test a few things on this setup, and we'll see if we do the printing with this one or with the next one. We'll see. But there will be a few other changes to this system again. To finally answer the age-old question, can you be masochistic enough to 3D print a Benchy in less than 1 minute? Let's find that out. But first, let's extrude some material. We heat it up. This is at 270, this is at 240. We're gonna extrude a perch one to flush all the pre-melted filament out of there. And then we're going with 10 grams of filament that should be on the tray later on. This will take approximately 27 seconds. This is at 300 cubic millimeters a second. All right, so go. All right. No skipped steps. Got the scale zeroed out. Let me cut that here. So should we call that under extrusion or just negligible amounts of measuring error? Guys, I'm pumped. This worked out absolutely beautiful. Let's run that again, just on the tray, and I will show you what the spools are doing up there. So again, bit of purging. Go. This is just dumb. Oh, it actually... Oh, frick. So I guess one filament strand couldn't handle the pressure and actually broke up there. I mean, it basically is just the filament being brittle, I guess, and maybe it was like tangled up somewhere, but it goes to show that these guys do have immense gripping power. It's just absurd what they can do. So again, just after this test, what you can see up here is the Teflon tape. It's absolutely tight up here. Tight, tight, tight. There is the smallest amount of material coming out straight from the nozzle thread. But yeah, just a piece of Teflon tape around that nozzle should be doing the trick. And again, back here also, no leaks whatsoever. So, what do you say about the results? For my part, I can say I'm pretty hyped about the results. It worked out just as I planned. Extrusion results are even higher than I anticipated. And I can run 300 cubic millimeters continuously all day, and it's just eating away filament, and there are no leaks and no squeaky noises, etc. So I'm really proud of having built that all by myself. There is really no thing to be found on the internet when it comes to these extreme appliances. When it comes to manufacturing and tolerances, I had to find all of that out by myself. But since we are the internet, I'm more than happy to give any of these information away for free. So you basically saw how I machined that. You could do that on your own if you have the proper hardware and skills to do that. But I think this would be a pretty good opportunity to test this in copper 3D printing. So I don't have the tools to do that, obviously. But I think if you would print like these two mold halves, you basically could generate all the threads, all the channels. You would have the right surface finish on all the channels, etc. So basically what you gotta do is retap the threads and lap these two parts so they mate up perfectly and make a tight seal. Let's talk about in the comments what I should do about this. I'm more than happy to give all those plans away and make this downloadable somewhere, so you guys could check this out too. But of course, we have to add that this is kind of a deep well to put money in. Again, a huge shout out to Bondtech and Slice Engineering for giving all that stuff free of charge to me. And I have no idea how that would have worked out with other stuff. But I mean, you could basically go ahead and you have an M6 thread that is connecting to a standard heat break. You could basically just throw a knockoff E3D V6 clone on there and use your standard whatsoever extruder and make it a Bowden setup or whatsoever. This is just the pure block for melting capabilities. And also the second heat zone isn't probably necessary for most of standard applications. So we could do that just by having an M6 thread at the bottom and exit into a regular nozzle. So tell me in the comments what I should be doing with it and how you would put this on your normal 3D printer. I guess this isn't for your standard Core XY or Cartesian machine where you have to move the tool head around because the copper is quite heavy, and even if you would do that out of aluminum or something, it is still way up there in weight numbers than all the other contestants. But if you have a system like me, which has a moving platform, you could basically integrate this there too. It's an open discussion here. Let me know in the comments what I should do about it. Also, again, there is a link to my Discord server, and all these information that you will be seeing in probably a week when I had the time to edit the video is already up there. There is a very active discussion about all the things, and there are way more pictures of manufacturing, etc. available than it is in these videos, even though they're that long by now. I think that's it for this week's video. I hope you enjoyed. It was quite a journey. I'm super hyped about the results here. And yeah, let's freaking 3D print something on this machine next time. See you guys. Bye-bye. Have you ever wondered what 300 cubic millimeters per second of filament extrusion looks like? Well, here's your answer. This is the Minuteman machine, and there's gonna be a build video of this beast of a Hotend next week on this channel.